Ted and Joe, they go to them by 1 because they don't need any probing. Okay. May, Ann, and Bob will need to have 3 and 4 and 5 operations because they have all have collisions. Okay. Say Bob here, it will hash to number 5. It will collide with Ted, and then collide with Joe, and then collide with May, and then collide with Ann, and ultimately defines an empty space. Okay. So here you see that the hash table of linear probing, well, it promised to be order of 1 constant time. When you look at the average here, it's actually closer to order n already. Okay. Now, let's look at double hashing. Now, double hashing, we say when they collide, they will go over a second hashing function. Okay. Now, if you look at the second hashing function, you will notice that May actually has to the second function is 6. Okay, this value is already plus 1, if I recall. Okay. Okay. And N will actually has to 4, and Bob will actually has to 1. Okay. Then according to a formula, I will use the original hash value and then add the new hash value. Because it's greater than 10, so it rounds back into 1. Okay, so it will put into 1. N actually get a 4, so 5 plus 4 get a 9. And Bob have a value of 1, so actually degrades into linear probing. So it will do 2 linear probing and then get to 7. Okay, so ultimately you will end up a table like that. Okay. Now, because everyone have a different stack due to the hash function. Okay. So you will see that it's much less clustered, okay? And the bracket indicate how many probing in double hashing they need, okay? For May is 2, Ted is 1, Joe is 1, Bob is 3, and N is 2, okay? Clearly, much closer to the constant time, right? Okay. Now notice that in all of my examples, the load factor, if you remember what load factor is, the number of occupied slots over the total table size is actually already half. Okay, so it's the limit. Okay, limited case. Whenever the load factor is almost half, then the hash table will have lots of collisions. So here you can see that double hashing is actually rather good. Okay, in preventing clustering, first reducing the amount of collisions. Okay. Now, so here the lookup, okay, is almost, okay, constant time, okay, I would say. And this is linear time, and this is linear time, okay. Okay? Now, in all these 3 cases, they are all implement the same dictionary, okay. In the dictionary ADT, the user will only see the same output, okay. But the only difference is that they really have different run times. Okay, so that's the lesson, okay, in the whole course. You have the same thing, you implement differently, you have the same output, some is longer, some is faster, some is shorter. Okay, now if N is very large, say 1 million, then you will notice a very huge difference. Okay, it's huge difference. Okay, so of course if this now you just see 5 and 1 is not a lot of difference. Okay, but if it is 1 million, then you see the difference. You get the idea, right? Now, for those of you who are not fast enough to keep track of the double hashing and things like that, you can try this by yourself at home. Because it's likely to be some test question, right? In some test question, likely I will give you some key, some hash function, okay? And basically, I will ask you to do some double hashing, okay? Very simple marks, okay? So please make sure you actually try this yourself. Yes?
Excuse me, I want to ask the number, you say the number of operations.
Oh, now supposedly I will count the amount of probing I need. So here, 10. I look up the key and then I go to the hash table, I really get it, I say it's 1. Okay.
In the double hashing,
Yeah.
the key is 1. The number inside is 2.
Which one?
In the double hashing, the first one may or 100.
May, yeah.
Yeah.
The first one may. Now, for the first one may, you will actually get a, originally get a 6. And then 6 you collide with Joe. And then you do the double hashing function. and then you could get a 5. So ultimately, you will get a 1 slot, and because 1 slot is empty, you will end up at slot 1. So we count it as 2 operations. It's kind of cheating, because you might say you do a double hashing function, and then you look up again. Okay? But well, in computer science, the unit cost is the probing. So that's why it's called 2. Yeah, that's why we call it 2. Yeah.
Is there a practical case when multiple times of hashing is favorable to us?
Multiple is
Like yeah, double hashing, can we have triple hashing?
now usually when you have double hashing, then most cases will be solved. If you really ask me whether there's triple hashing, luckily we have the internet. Okay, triple hashing. Well, the part called triple, so I think you have triple hashing only when in security. Because last time we said hashing is also related to security, right? So we can have that. Now, for example, you can see there is a security risk. Say supposedly now you run a game, online game, in which the user account are hashed to a table. Say you use a very lousy function, okay, that has a lot of probing. Now I suddenly know that what your hashing function is. So what can I attack? I can have a robot that creates an account name that hashes to the same place every time. Okay, and then your server can get completely stored just because the hashing is order of n. Say you have 1 million users. Okay, supposing I suddenly have a hash function that has to some specific player, and then you keep hashing it, then you will slow down every operation of that player. Because I need to look up a lot of these players' things, right? So this is also a kind of attack. So you can imagine when you have a security concern, you don't want people to know your hashing function, and you might want to hide your hashing function or do extra hashing so that people can never, attack you in some way. Okay? So whenever you are interested in future, you will take some security course and you realize that you have a lot of hashing. Yes?
But brute force hashing attack, but preventing from brute force
Yeah.
attack really costs computational time, which is why we don't want to use it in
Yeah, most of the time in this case. Now, another thing I will caution you. In my hash functions, you notice that I always use prime numbers. Now, but the reality is that in real world, hash functions, this Java hash function for string is actually very primitive. Okay, I don't teach those functions because those functions require very strong mathematical backgrounds now. Okay, if you're interested, you can look up modern hash functions, which doesn't look exactly like this. Okay, in most of the web operations and things like that, the hash function is far more interesting, and they give a much better guarantee. Okay, so if you look at this hash function, you realize that, well, it's still very insecure or it's not very primitive. But no, I assure you that because of this decade of internet, we have hash functions that look very interesting, and they are increasingly hard to crack and resilient much better, to many different cases. You look at this Java's hash function, right? This is a joke, right? You look at all the hash will hash to the same place. So it's rather different. It's rather different. But I have to teach you this hash function because these are the hash functions you can use in labs. Okay, my apologies. Okay, any more questions? Good questions? Now, if you have no questions, just remember that you can actually try this at home. Okay, try this again. Okay, the point to make here is that ultimately whatever I choose to use, it will end up the same in terms of the user. Okay, this is a bit different from the linked list and array because they don't have many variations. For the hash table, we have so many ways to do the same thing. Right? We can choose different hash functions. We can choose different double hash functions. We can even have different ways of terminating a probing. So it's rather different. Say another issue that some of you have encountered, I hope you haven't, is that if your probing doesn't stop, right? In the lab, I have lookup that is 999999. Okay, so some of you may have caught off guard and then run into infinite loop. Right? You go probing and then it never stops. Now, how probing stops? In most of the cases, if you have a probing and then you keep probing, you will stop when you somewhat close to order of the time table. Now, for linear probing, it's very obvious, right? If you linear probe from 5, 6, 7, 8, 9, 0, 1, 2, 3, 5, then you know that you need to stop, right? That is obvious. But for quadratic probing, some of you may wonder, right? Quadratic probing, when do I stop? Well, usually you stop when you have gone through the table size. Okay? You know that by some probability that you probably have gone through all the slots. Okay? Now, but in reality, you will always know that when you insert, you're already doing a lot of collisions. Then, in most cases, we will do some operation. Now, in most of the time, we do an operation called rehashing. What does it mean? Now, I insert a key into a dictionary. Or in some case, okay, I know that I'm in a hash table. I insert a key into a hash table. Then I realize that I need to do a significant amount of probing, okay, to insert that key. Now, then I know that my table is just not good enough. Okay. Now, in this case, usually, we will increase the table size. When you increase the table size, the load factor will increase. The amount of load, the collision will decrease. Okay. It's just easy to imagine. In your lab, you have a table size of 10, right? If you have a table size of 100, then you'll notice that the probability of collision is very small. Okay. I don't know how to say it in English, but in Chinese, we have a saying. Okay. Now, I think the English again is very bad. Can I edit this suggestion? Anyone who has that? Now, in Chinese, we call it, okay, when you have money, sorry, the translation is very literal every time. When you have money, you become naughty. Now, anyway, it seems that means when you have money, you will do anything, right? You can do anything. Oh, I like that. I throw this away. Okay, I buy 3 cars. I don't like one. I just throw it into the sea. Okay, so when you're rich, you can do anything. Now, in data structure, we have the same concept. And what is money? Money is space. Okay, we need to change that back into English. Okay. In data structure, when you have space, you can do anything. Say I create a hash table of 1 million size. Well, who cares, right? So it is what we call a very advanced concept, space-time complexity trade-off. Okay? When you have lots of space, you can do anything very quickly. Okay? But of course, in reality, you know that doesn't happen, right? You have an online game with 1 million users. How large the hash table can be, right? If you can really have such good hardware to have 1 billion in size, of course you can be very quick. Okay? But in reality, the more space you have, the faster your operation can become. Now this is not very obvious in linked lists and things like that, but in dictionary, you realize that it's very, very obvious, right? Just now the collision. The whole reason the collision is so bad is because the table size is 10. Right? You modulus 10. Okay? You modulus 100, modulus 1000. Nothing, okay, it will happen, okay. Every key will have only one operation, simply constant time. So that's something you put in mind, okay. Now, I'm not going to teach the space-time trade-off in this course because it's very hard to find examples at this level, okay. But in the future, when you do networks, securities, and things like that, you will find that often it is these two trade-off. The more space you can afford, the faster your growth can be. Okay? The less space you can afford, then now look at this. You can see easily the space trade-off. Look at the linked list. The linked list have the least space. You just have 5, right? You just need 5 slots. But then the time is the largest, right? Here we have 10 slots, and the time, okay, is slightly slower, faster. Okay, so you see the trade-off already. Okay, so the more space you can contribute, okay, the faster you can afford. Okay, any questions? Now, So in reality, when you do a hash table, the moment you find that you have a lot of collisions, you need to double the size. So in your lab, I do the hash table as a fixed array. That is lazy. Okay? Ultimately, you need to dynamically allocate some memory. When you find that the hash table is almost full, you need to reallocate a new memory and then put everything into the hash table again. Okay? So this is what we call rehashing. Okay? I'm not going to ask you to try that because whenever I ask you to malloc, there will be so many bugs. So, but just keep in mind, okay? That's what people do. So that's why you can keep putting in a key. Initially, they will assume that, say, I give you a hash table of 10. And then when you put many keys, then they double it, and they double it, they double it, okay? So that's actually how hash table works in reality. Okay? Now we will take a small break, and then we will talk about some more advanced ADT to make, okay? 2 minutes break.